Hi, this is part 2 of the lesson on the limit of a function. So let's continue with how to evaluate limits by reading a graph. So here's our example. So I want to evaluate the limit as x approaches 3 from the left of f of x. So I go to the left of -3 and I follow the path of the y values. And you can see that as I get closer and closer to 3, my y value is approaching the value of 2. So the limit as x approaches 3 from the left is equal to 2. Now I need to evaluate the limit as x approaches 3 from the right. So as x approaches 3 from the right, again, if you follow the path of the function, I just need to move this down a little bit. If I'm on the right side of 3 and I follow the path of the function, well, that means I'm up here, and that appears to be getting closer and closer to the value of 3. So the left-hand limit is 2, but the right-hand limit is 3 as x approaches 3. And so what that means is that the limit does not exist. That's what this means, that the limit as x approaches 3 of f of x does not exist. And then the last part of the question is to evaluate f of 3. Well, if you look at your graph where x is equal to 3 and look at what the corresponding y values are, there's 2 open circles above 3, which means that f of 3 is undefined. So if one of them had been colored in, that would have been your answer, or if you had had a solid point somewhere else on the graph, like for example, up here, if I had a solid point, then your answer would have been f of 3 equals 5. But there is no solid point that corresponds with the value of 3. All right, so here's another graph. We want to evaluate the following for the given graph of g of x. And we have that we want to evaluate the limit as x approaches 0. And so as x approaches 0, you need to evaluate that both from the left and the right. So from the left side, if I follow the path, this looks like it's going towards 2. On the right side of 0, it's also approaching 2. So the limit as x approaches 0 of g of x is equal to 2. So the limit exists. And that's again because the left and right hand limits are the same. But g of 0 does not exist. There is, again, no solid point that corresponds with the x value of 0. There's an open circle at 2. So although the limit exists, the function does not. Now we're going to look at the limit as x approaches 1. Well, as x approaches 1 on the left side, this appears to be going towards, again, I think I'm not quite showing the whole picture here. Yeah, I'm not. Let me get rid of this. So as x approaches 1 from the left, as I get closer and closer to 1 from the left, this is approaching the value of -1. That's right here. As x approaches 1 from the right, that's getting closer and closer to this value, which is 0. And then again, the limit does not exist because the left and right hand limits are not the same. And g of 1, well, in this case, g of 1 when x is 1, your g value is up here at 2. So the limit does not exist, but the function does. So now we're ready to move on to 3. So the limit as x approaches 3 from the left, I'm on the left side of 3 and I follow the path of the function. That is approaching a y value of 0. The limit as x approaches 3 from the right, I'm on this piece, and that's getting closer and closer to the value of 1. Again, the limit does not exist because the left and right hand limit are different. And if I were to try to evaluate g of 3, well, when x is 3, your solid point is right there, so g of 3 equals 0. Okay, so let's move on to the next example. We want to sketch the graph of the function that satisfies the following conditions. So we do not have a graph here. We need to sketch it based on the conditions that are given. We want to show a graph where the limit as x approaches 0 from the left is equal to 2, 0 from the right equals -1, and f of 0 equals 0. Right, so the only point we know for sure is that we have a solid point at the origin. When x is 0, y is 0, so we have a solid point. Now we have to show a graph where you have a left-hand limit going to 2. So suppose here, this is the value 2, and a right-hand limit approaching -1. So let's suppose this here is -1. So from the left side, I need a graph that's getting closer and closer to 2. And that you could draw anything you want there, a line, a curve. And on the right side, it's approaching -1. So I'll put an open circle here and I'll make this one a curve. And so here's an example of what that would look like. The easiest and most direct way to evaluate a function is by direct substitution. And so here's an example. If a is in the domain of f of x, then as x approaches a of f of x, that's just equal to f of a. So what that means is that if a is in the domain, you don't have to sketch the graph or draw or use numerical values with all those decimals that we did in part 1. We can just plug in the a in for the x and get the value of the limit, because the limit value and the function value will be the same. So here's an example. I have the limit as x approaches -2 of the square root of 5 plus x squared. So -2 is in the domain. In fact, all values of x are in the domain. No matter what you plug in, you're going to get a positive result inside of that radical, which means no imaginary numbers. So instead of plugging in numbers like -2.0001 in here and creating a table, I can just go ahead and plug in -2, which is what we did here. And so you get 5 plus 4, which is square root of 9. And so your limit value is 3. So that's only a special case where you can do direct substitution, where it's in the domain. You don't have to do anything except plug it in and evaluate. So here's a piecewise function. We want to sketch the graph and evaluate the following limits. So the piecewise function is defined to be the line x minus 4 for values of x less than -2. It's defined to be the parabola x squared minus 1 for values of x between -2 and 2, but including -2 because of the less than or equal to there. And it's equal to the line 2x for values of x greater than or equal to 2. So I graphed it here. This is the x minus 4 part of it. So I plugged in -2. That gave me this point here, -6. That's an open circle because it's less than. And then I just picked another value less than -2, such as -3 or -4. And so you would get another value down here and connect the 2 points going to the left. And there's your x minus 4. X squared minus 1 is a parabola with a vertex at 0, -1. So I plotted the vertex, and I also plugged in -2 and 2 into x squared minus 1, and those both give you a value of 3. So here, -2, 3 is solid because it's less than or equal, but here at 2, 3, it's open because of the only less than sign, not less than or equal. And then finally, I'm ready to plot 2x. 2x is again a line. So I plugged in 2 in here and I get 4. So that's that point. And then I plugged in 3, something greater than 2, plugged it in. That gave me this point 6. Connect the 2 points going upward and to the right. And that's the line 2x. That's the third piece. So now we can evaluate these limits. I have the limit as x approaches 2 from the left. -2 from the left. So -2 from the left means that I am on this line. Those are values less than -2. So as I get closer and closer to -2 from the left, my y value is approaching -6. Then I evaluate the limit as x approaches -2 from the right. When I'm on the right side of -2, I'm looking at this piece, the parabola. So again, by direct substitution, I can plug in the -2 right in here, and that gives me a value of 3. And you can also see it on the graph. When I'm on the right side of -2, my y value is +3. All right, and then the limit as x approaches 2 from the left. 2 from the left means, again, I am on the parabola, and 2 from the left means I am approaching this point right here, which is, again, a value of 3. And 2 from the right, well, this is the right side of 2, greater than or equal to 2. I can do by direct substitution, plug in, and that gives me 4, which again corresponds with that point right there on the graph. So you can evaluate it by looking at the graph, or you can evaluate the limit by considering the different parts of the piecewise function, whether you're on the left side or the right side. All right, so here we want to evaluate the limit from the left and from the right as x approaches 5 of 3 over x minus 5. So again, we know that in this case, I can't just plug in 5. I can't do direct substitution because then I would have 3 over 0. That's undefined. So we can't do that. I graphed it so that we could understand this a little bit better. So this graph has an asymptote at 5. And when I am on the left side of 5, this graph is approaching -infinity. When I'm on the right side of 5, this graph is approaching infinity. So it's easy to see if you have a graph, but if you don't have a graph, you can think it through numerically. So let me show you an example. If I'm on the left side of 5, I'm going to pick a number to the left of 5 that's very close to 5, 4.999 minus 5. That gives me 3 over -0.001. So when you're dividing 3 by a negative number like this that's close to 0, that becomes a very negative number. It's approaching -infinity. Similarly, on the right side of 5, if I pick something like 5.001 minus 5, that'll be 3 over 0.001. And 3 divided by a very small positive number becomes a very large positive number. So you can plug that into a calculator and play around with different numbers close to 5 to the left and right of it, and you'll see that the number goes to either plus or minus infinity, depending on which side you're on. Okay, so here are 2 more examples. These are 2 functions that are, again, related. These are inverse functions. I want to evaluate the limit as x approaches 0 of e to the x, and then I'm going to evaluate the limit as x approaches 0 from the right of ln of x. Now, with this one, it's very straightforward. E to the x has a domain of all real numbers, so 0 is in the domain. So I can evaluate this by direct substitution by just plugging it in, and that's e to the 0, which is equal to 1. You can also see it on the graph. This is the graph of e to the x right here. As I get closer and closer to 0 on the left and right side, the path of my function is going towards the blue point, which is equivalent to the number 1 on the y-axis. So with the natural log, the reason why I'm only taking the limit as x approaches 0 from the right is because the domain of my natural log is only from 0 to infinity. Natural log is undefined. Sorry, it's open circle. It's not defined at 0. Natural log is only defined for positive numbers. At 0, it's undefined, and at negative numbers, it is also undefined. So as x approaches 0 from the right, your graph is approaching -infinity. Here, it is helpful to know what the graph looks like in order to evaluate that, and you should know both of these graphs, e to the x and ln of x. So as x gets closer and closer to 0 on the right side, you can see that your function is approaching negative infinity. So our second limit does not exist. So when it approaches plus or minus infinity, that's not a finite number, so the limit does not exist. Okay, one more problem where we are sketching. So we want to sketch the graph of the function that satisfies the following conditions. We have the limit as x approaches negative 1 of f of x equals 3. The limit as x approaches 2 from the left. Remember, this means negative 1, but this means 2 from the left. So the limit as x approaches 2 from the left of f of x approaches negative infinity. 2 from the right approaches infinity. And f of negative 1 equals negative 2. Okay. So this is the only point that we really know for sure. F of negative 1 is negative 2. I went ahead and plotted that. But the limit as x approaches negative 1 is going towards 3. So that means that on the left side and the right side of negative 1, I have to show two pieces of a graph that are getting closer and closer to the number 3. But 3 has to be an open circle because I already have a solid point here. You can't have two pieces of the graph on top of each other vertically because that wouldn't be a function. It would fail the vertical line test. So now we have to incorporate this piece of it. So it appears that 2, at x equal to 2, we have a vertical asymptote, which I drew in this hot pink line going down this way. As x approaches 2 from the left, it goes to negative infinity, so that's this piece here. But as x approaches 2 from the right, it's going towards positive infinity, so that's this piece here on the right. So it takes some practice to get used to these sketching problems. So make sure you understand the two that I did in this lesson before you try doing others like that. So that's it for this lesson. Try the homework. Good luck.